Well, thanks, Sutrit, for inviting me here. It's a pleasure to be here, especially on such an auspicious day, and great tea. So as the title says, of course, I'm going to try to tell you a little bit about context structures on high-dimensional manifolds. A little outline of what I'd like to do is I'll begin by just giving you the basic definitions of a context structure, which seem a bit abstract, and one might wonder why you would study them. So the next few sections, I'd like to kind of talk about where context structures show up kind of in the natural world. If you're not a mathematician, why you might actually run across a context structure someplace. A little bit of a history about kind of where they first appeared, other contexts in which context structures show up. Finally, give a little bit of motivation kind of from a more modern perspective about what context structures have done for me lately, or the math world lately. And finally, I'll get to the last two sections. We'll be discussing a little bit more about the existence question, which is the main result I'd like to present at the end today. So let's just get started with the basic definitions. First of all, a context structure only exists on a closed manifold. You don't necessarily have to assume oriented, but I am going to assume oriented just to make life easy for us. So let M be a closed, oriented, odd-dimensional manifold. An oriented hyperplane field is a context structure if you can realize it as the kernel of a one form such that it satisfies this condition, which is a kind of a non-integrability condition. What it means is the context structure will not be tangent to any hypersurfaces along any open set. It actually says a little bit more than that, but I'll just leave it at that. So this afternoon I explained a little bit more about the integrability, the maximal non-integrability. So let me start by giving you an example. So this is kind of the classic example of a context structure on Euclidean space. So of course I'll draw the pictures in R3, but in general we're of course talking about any odd-dimensional Euclidean space. So if you just look at the kernel of this one form, one can easily see that it satisfies the contact condition, and at least in dimension 3, it's very easy to understand this picture. So notice when n equals 1, so in 3 dimensions, if you're at the origin, 0, 0, 0, then the contact hyperplanes, you just got the kernel of dz, so they're spanned by the vectors in the x and y direction. So it's just a plane parallel to the xy plane. When you move out to y equals -1, by the way, if you look at this, you might kind of wonder, why do I have the y going back into the board? It's because I want an oriented coordinate system. So y equals -1 is out here toward us. Then the contact planes are spanned by, well, you still got d dy in there, but now you've got the vectors pointing the x in the x direction minus the vector in the y direction. So what's happened is the contact planes have stayed tangent to the y-axis, but they've tilted 45 degrees. And as you move out for different y values, you basically see that the y value that you're at just tells you how much the plane has tilted. So you start out with this horizontal plane, and you move along the y-axis, and you tilt 90 degrees as you go out toward infinity, and 90 degrees the other direction as you kind of go back toward, well, sorry, I guess minus infinity in this direction and plus infinity in that direction. And finally, notice that this form is invariant if you translate in the z direction or any of the x directions. So once you understand this ray, you just repeat it infinitely often, kind of on all rays or lines perpendicular to the xz plane. Just start out horizontal and twist 90 degrees as you move to infinity in either direction. So this is kind of the standard context structure, and there's this wonderful theorem of Darboux that tells us that all context structures locally look like this picture. So once you've understood this picture, you understand the local picture of any context structure. And in particular, we could have defined a context structure simply to be a hyperplane field that locally looks like this. So one other definition we're going to need throughout the talk is, as is always the case when you're studying manifolds, it's very common you want to understand subsets of the manifolds, submanifolds that have certain nice properties. And for context structures, the nice submanifolds you want to study are the Legendrian submanifolds. And so those, if you're in a 2n plus 1 dimensional contact manifold, a Legendrian submanifold is simply an n-dimensional submanifold that's always tangent to Xi. Remember I told you that Xi is maximally non-integrable? It turns out that n is the maximal dimension you can have for a submanifold to get something that's always going to have its tangent planes lying in the contact hyperplanes. So that's a Legendrian submanifold. Unfortunately, we're probably not going to have time to go into a lot of detail about this, but when you're looking at Legendrian submanifolds of R3, so R3, that means your Legendrian submanifolds are one-dimensional manifolds. In other words, they're knots. We're talking about knots in R3. Well, you can project them onto the xz plane. And let me maybe move back to this picture. So, well, maybe we can just see it here. So when you project onto the xz plane, if the knot is tangent to the contact structure, it satisfies the z prime coordinate minus the y coordinate times the x prime. The derivative of the x coordinate is equal to 0. So in other words, the y coordinate is equal to just the slope in the projection, in the xz projection. So when you see this picture, this really is a three-dimensional picture because, for instance, at this point, the slope in the xz plane is 0, so the y coordinate is 0. And at this point, the slope is -1, so the y coordinate is -1, and so on. Notice you see these strange kind of cusps showing up. Well, that's because, of course, since the y coordinate is recovered by the slope in the xz plane, you can't have any vertical tangencies. If you had a vertical tangent, that means the y coordinate would be infinite, but that doesn't happen. So that shows up with these cusps. I should really emphasize that our Legendrian knot is still actually a nice smooth knot. It's just when we have a smooth knot, there are certain projections that will have kind of singularities in them. And in fact, they're forced on you by the condition that you're tangent to the contact planes because you can't have the vertical tangencies. And so here's a few typical examples of Legendrian knots in R3. So again, they look like standard knot diagrams, except they have cusps instead of vertical tangencies. And whenever you have a crossing, the crossing with the more negative slope, the crossing with the more negative slope is in front, because remember, -y is in front with the way I've set things up. Well, there's a nice result that says if you have an n-dimensional submanifold in a contact manifold, you can always kind of C0 perturb it to make it tangent to the contact plane, so to make it Legendrian. And if you understand these pictures of the projections, admittedly we didn't spend much time on them, but if you understand these pictures, it's easy to prove that. Because suppose you just have any line sitting in R3, project it, the tangent, the slope of the projection doesn't recover the y coordinate in general, but if you kind of put these little zigzags in, you can arrange the slopes to be arbitrarily close to whatever the y coordinate was, and that means that when you recover the y coordinate using this, you'll actually have a Legendrian knot that will actually be very, very close to the one you started with. So you can always C0 approximate any knot with a Legendrian knot. OK, so these are the basic definitions. The first time you run across it, certainly the first time I ran across it, it seemed fairly abstract, and you kind of wonder, where does this show up? And so what I'd like to do now is try to convince you that they actually show up very naturally in several places. So this is maybe one of my favorite examples. If you look it up in books, this example is actually called the space of contact elements, or contact elements. But let me kind of describe it in kind of a natural situation. So suppose we're trying to model a physical situation. In the physical situation, it could be, say, the front wheel of a bike or a car, or at least the way I'm going to think about it now is, suppose we're trying to skate around a skating rink and model the motion of the skate on the ice. So it's just going to be one skate, so we're only skating on one foot here. So what do we have to know to understand the motion of the skate? Well, first of all, of course, you have to know where you are. So you have to know the x, y coordinates. The next thing you have to know, of course, very important when you're skating, is what direction is the skate pointing. So you need to know some angle. So basically, you think about the heel of your skate down here, and you have the angle that the skate forms with, say, the positive x-axis. So the configuration space is simply R2 cross S2. So if you have a skate moving around the skating rink, it's always at any time going to be some point in that space. So how does the skate move? Well, one thing that happens is, of course, if you're kind of sitting at a point, you can actually pivot your skate and point the skate in any direction. So that's not too hard. The more important constraint on a skate is that you can only move in the direction the skate is pointing, right? You can't kind of slide sideways against the blade of the skate. Well, maybe some people can, I can't, but most people have to move in the direction the skate is pointing. So if we have a path, gamma, that represents the motion of a skate, so I'm telling you it's basically its position and its angle at every point, then the motion of the skate, if I can, 2 translates into this condition, right? That the direction that you're moving, so the y coordinate, the derivative of the y over the derivative of the x, is determined by the angle given by the given by the direction the skate is pointing. So another way to rephrase that is, well, actually, let's just consider this contact structure, the kernel of this one form, and one can easily check that this is a contact structure. And now one can further check that if gamma represents the motion of a skate, it satisfies this equation, which you can rewrite in terms of being in the kernel of this. So in other words, the path is a motion of a skate if and only if it parameterizes a Legendrian curve. So we've kind of rephrased this geometric, or this physical problem in terms of a geometric problem of understanding when the curve is Legendrian. So there's a great application of this. So the application of what we just discussed is that you can always parallel park your car. And well, actually, I personally know counterexamples to that statement. So I've run into problems with this myself. So really, the real theorem here is you, or at least someone, can, in theory, park your car if the space is bigger than your car, right? We have to be precise. OK, so how do we prove it? I mean, well, so suppose you've got your yellow car. You're trying to park between your red and your green cars. So by the way, as is frequently the case with mathematics, we're not maybe going to get the whole car in the right place. We're going to get the tire in the right place, OK? And hope the rest of the car follows well enough. So, well, you have the desired path for your front wheel. You want the front wheel to move to that spot, right? That's a path. Well, remember, we can always Legendre approximate. Well, given any small neighborhood, we can C0 approximate that path in that neighborhood by a Legendrian path. And so the front wheel just has to follow that Legendrian path, but that's a Legendrian. It's an acceptable motion for the front wheel, so you can do it. And however small this is, you've got the epsilon. This space is epsilon bigger than your car, so this is a epsilon over 2 neighborhood, and you just make sure you do an approximation that small. Okay? So again, in theory, you can park the car. So again, contact geometry has real-life applications, right? OK. Well, as I said, I'd like to kind of give you an idea of kind of when contact structure showed up. This actually got a very, very long history. When I was looking back, I mean, study math, you frequently don't know the history of things. I was looking back trying to find the first occurrence I could find of a contact structure, and it actually appeared in this guy's work. Anybody recognizes him? It's actually Sophus Lee. So in 1872, he published this paper. And in the paper, he talked about basically a contact transformation. I'm not going to try to pronounce it in German, but contact transformation. And he actually wrote down the standard contact structure I gave you, like on the second slide. So that's the first time I think the standard contact structure on R2n+1 appeared in a paper. And if you translate the title of the paper, basically he's trying to classify first-order partial differential equations. And he's trying to talk about how would you go about solving first-order partial differential equations. And so what I'd like to do now is give you a little bit of an idea about what was his idea. How did he think to go about trying to solve these equations? So in modern terms, this is what he suggested you do. Well, so first of all, what is a first-order partial differential equation? You have some function from R2n+1 to R, and you're looking for some function z that satisfies this. You plug in the coordinates, the derivatives, and the value of the function, and it satisfies the equation. So what are we going to do? Well, notice this is equivalent to the following. So instead of looking for the function z from Rn to R, I could look for a function u from Rn to R2n+1. And well, it satisfies f composed with u is 0, and the image of u is Legendrian. So what does this really mean? Well, if the image of u is Legendrian, and remember we're using the contact structure that I talked about on the second or so slide. So what is this? This thing says what? It says the yi coordinates are determined by the derivative of the zth coordinate with respect to the xith coordinate. So in other words, if you're Legendrian, that means the zth coordinate of u is going to be something that satisfies this equation if u satisfies that. Okay? So basically, you've turned this PDE, this analytic problem, into two different problems, an algebraic problem and a geometric problem. Well, algebraic if f happens to be, say, an algebraic equation. But, right? So Lee's idea was you should look for diffeomorphisms of R2n+1 that preserve the contact structure. So these contact transformations that I had on the previous slide, that simplify the algebraic equation. So if you preserve the contact structure, that means you preserve this condition. So you preserve that your u actually would solve an equation, or would be the z coordinate of u would be a solution to the equation. And if you simplify this equation, well, you got an easier problem to solve, an easier algebraic problem to solve. And he actually showed for many classes of equations, you could actually find transformations that would turn your complicated equation into something where you could just kind of, staring at it, solve the equation. So that was his idea. So where else did contact structure show up? Well, 1 year later, a paper was published by Gibbs, where he was studying thermodynamics. And so the setup is the following. So given in thermodynamics, you basically got these 5 quantities that kind of determine a system: the internal energy, temperature, entropy, pressure, and volume. And they're subject to this equation, which of course, from our perspective now, it's clear this is just the standard contact structure where I've changed some variables. Gibbs reinterpreted the first law of thermodynamics as the equilibrium states of a thermodynamic system are Legendrian submanifolds. So in all honesty, I'm happy to talk to anybody about any of these applications after the talk, except for this one. This is the one I actually haven't spent enough time to understand really well. But this is one of the first times that contact geometry showed up as a way of formulating equations. By the way, I'm not saying, as far as I know, Gibbs didn't actually have this formulation using the words of contact geometry, but he essentially had this formulation without using the words of contact geometry. So I told you the first occurrence I could find of a contact structure was in 1872 with Sophia Lee's work. Well, we're now going back to 1690. A lot of people kind of attribute Huygens to be the first person that really kind of had a principle that should be expressed in terms of contact geometry, even though he didn't. So there's no papers that he wrote that say anything about a contact structure, but there's a very nice way you can reinterpret his ideas in terms of contact structures. So, so this is as follows. So the idea is he wanted to understand the propagation of wave fronts. So in other words, you think about, you got, say, a point source of light, and you flip on the light at some time. Then even though it travels very, very fast, it doesn't illuminate everything immediately. There's kind of this way, there's this front that separates the light from the dark, right? And that kind of propagates out. And what he said basically is that if you have this wave front, at one point in time, if you look at time epsilon further, and you look at all the envelopes of circles of radius epsilon about the points on that first front, you'll get the next front. So kind of you've got this propagation rule or law that he could actually explain quite a few phenomena in optics, with this idea. And in modern terms, basically it says waves or the wavefront of, say, a light source propagates according to the Rabe flow of their Legendrian lifts to the sphere bundle. I'll talk about Legendrian lifts later on, but I don't want to spend too much time on this right now. But this is the modern or contact geometric interpretation of Huygens' principle. So another place where contact structures show up fairly naturally is in Riemannian geometry. So it turns out that, well, of course, anybody that studies Riemannian geometry, one of the first things you run across in a class is the idea of a geodesic flow. So if you take your tangent bundle, you look at the unit cotangent bundle, then you've got the geodesic flow on the unit cotangent bundle, which of course determines the geodesics in the manifold and quite a lot of the geometric properties of the underlying manifold, various things about curvature and so forth. Well, it turns out that if you look at the unit cotangent bundle, then there's a natural contact structure on there, which I'm actually going to tell you a little bit more about in maybe 10 or 15 minutes. And on that unit cotangent bundle, there's what's called the Rabe flow, which is a flow that basically preserves the contact planes. It's a flow that's transverse to the contact planes and preserves them. And it turns out that this Rabe flow, this contact geometric quantity, is equivalent to the geodesic flow. So there's an isomorphism between the tangent and cotangent bundle using the metric, and the Rabe flow is sent to the geodesic flow. So if you want to understand properties about the geodesic flow, you can study the Rabe flow instead. And quite a few properties or problems in Riemannian geometry can be translated into contact topology if one is inclined to do so. So another place they show up naturally is in Hamiltonian and symplectic geometry, Hamiltonian mechanics and symplectic geometry. This is maybe one of the most well-known kind of places that contact structures show up. I, again, decided maybe not to spend too much time on it here, so I'll say that and move on. And the last application or connection with contact geometry to something else is fluid mechanics. And this I thought I'd just spend a moment or two on because I actually had a little bit to do with these connections. So Robert Greist and myself, maybe 10 or 15 years ago, were looking at some questions in fluid dynamics. And if you have a perfect incompressible fluid flow, that means it satisfies Euler equations, so these two equations. So incompressible is just that you preserve some volume form, and this is the Euler equation that kind of, well. And there's two sort of questions you can ask about these sort of equations. One is you can say, can you find a U that solves these equations? So that's a PDE problem. Another problem is, suppose you have a solution, you can ask, what are the properties of the dynamics of the flow of U? And so that's the question that we were interested in. Can you say something about the flow of, can you say something about a fluid flow? And there are various results that we could prove. One of them is, for instance, that if you take any metric on S3, so you've got S3 with any geometry at all, and you look at fluid flowing around on S3, you can prove there's always a periodic orbit. So in other words, you've got this fluid flow moving around the universe somehow. There's some place you can drop a particle and it will come back to itself. There's also various other forcing results about fluid flows in solid tori that's related to plasma physics. There's an idea of hydrodynamic instability. So if you have a time-independent solution to this, you can ask, is it stable? In other words, if you perturb it a little bit, does it actually come back to itself as time progresses? And we could actually prove that for a generic metric, that doesn't ever happen. Every steady flow is unstable. Well, every stable, maybe I should say every Beltrami stable flow. It's a special type of stable flow, but it's a very common type of stable flow that people study. And again, all of these results really rely on significantly on results in contact geometry to prove. So with all these things said, you can see they recur over and over and over again in many kind of geometric settings. And this actually led one of the pioneers of modern contact geometry, Vladimir Ono, to make the following statement. So he, on several occasions in several different books, you can see Arnold arguing that contact geometry is all geometry. Many geometric problems you're going to come across, you can rephrase in terms of contact geometry. And he advocated you should do it. Now, I don't know how successful he was in a lot of things. We'll actually see some of his conjectures later on that would imply very interesting things about topology. But again, from some perspectives, this is actually kind of ubiquitous, subject that maybe isn't as well known as some others. Anyway, I'd like to move on and now tell you. So everything I've been telling you about is kind of where it showed up in history. But one question is, it's been around for so long, why isn't it kind of better known? It's because, well, there wasn't really a good theory of contact structures until maybe starting sometime in the late 70s or somewhere in the 70s or 80s. And it's been developed quite significantly since maybe the mid-90s. So it's a relatively young field as far as having kind of real mathematical results associated with it. And I'd like to tell you about some of the applications now. So as far as I can tell, the very first hint that contact structures were going to tell you something really important about the topology of manifolds was this result of Eliashberg's. Back in 1992, he reproved Serfs' theorem. So Serf has a famous theorem that said any diffeomorphism of the three-sphere extends over the four-ball. A lot of times when you tell people this, you think, of course, this is completely obvious, because you're thinking about, say, S1 or S2, and here the results are not too hard to prove. The result for S3 is very hard, and as you go to higher spheres, it's not even true. But the result for S3 is quite hard. Serf's original proof, it's one of the Springer-Verlag kind of lecture notes in math series, and it's on 600 pages. It's a huge, very, very long, complicated proof. Eliashberg's proof is a paragraph. OK, that's not quite fair. It's a paragraph that relies on 3 or 4 other papers that when you add them together is several hundred pages. But the nice thing is all these other papers were developing ideas in contact geometry in their own right. It wasn't to attack this problem. But once you had these properties, you could very, very easily and rapidly, well, maybe not with every last detail, but rapidly prove Serf's theorem. So again, this is one of the first applications to topology. And it's one of the things that kind of gave an indication that maybe these contact structures are going to have something to say about the topology of manifolds. And that's kind of been bared out over time. So using Heegaard-Floer homology, Ajbaf and Szabo were able to prove that the genus of a knot is detected, well, by Heegaard-Floer homology. And a key ingredient in the original proof, at least, was contact geometry, where I do think, I guess, after the fact, there are sutured manifold versions of this result, but the original proof uses contact geometry. Similarly, the fact that Hegardt-Floer homology detects fibered knots was proved by Gagini and Ni. And again, Gagini's original idea was very, very contact geometric in spirit. Ni kind of reinterpreted a little bit more in a sutured manifold way. And Gagini's proof was originally for genus 1 knots. Ni did it in general. But again, the inspiration for how Ni did it came from contact geometry and could be expressed purely in terms of contact geometry. So maybe a result, as far as I know, doesn't have a proof except using contact geometry, is a proof of property P for knots that Kronheimer and Rofke gave. What? What? Sorry, this is true. That was that the first proof? It was? I see, I see. Okay, there you go. What? Oh, really? It's, oh, sutured instanton. Okay, okay. So they have kind of removed that away. Okay, so this was not the original proof. Sorry about that. We should say the original proof, right, is Perelman. But I guess these were coming out, I don't know. The flurry of ideas seem to be about the same time. But anyway, because of course also their proof existed before 2004. It was published in 2004. But anyway, I don't remember when it came out exactly. Anyway, but again, they were using instanton homology, and they were using, again, kind of symplectic and contact ideas at a crucial step along the way. And again, I should maybe remind people, what is property P? It's a very old conjecture about knots. It was a way to kind of get at, well, it's supposed to provide evidence toward the Poincare conjecture, which also we know to be true now, but not through the surgery type methods. The idea was that if you have a knot and you do surgery on it, you can ask, does the resulting manifold actually have a non-trivial fundamental group? And property P was the conjecture that, well, property P states that a non-trivial knot, the property P conjecture says a non-trivial surgery on a non-trivial knot yields a manifold with non-trivial fundamental group. There we go. And great. But again, that also does. And again, there's surgery characterizations of the unknot, trefoil knot, and figure 8 knot due to Advat and Szabo. I don't remember, was 2006 for the trefoil and figure 8, or was that that was probably the trefoil and figure 8, and that was probably much earlier. Yes. Anyway. Okay. So these were basically various results to topology. I'd actually like to tell you about a kind of a program that in some sense Arnold kind of put forward for using contact geometry to study kind of all sorts of topological problems. So this involves kind of what's called the conormal lift of knots. So I'll start with just looking at a manifold. So the idea is, given a manifold, you want to associate a contact manifold with it so you can use contact geometric ideas to study the manifold. And the idea is the way to go about it is fairly simple. So first we fix a metric on the manifold M and let W be the unit cotangent bundle. So you look at all the unit covectors. Of course, a metric on M gives you a metric on the cotangent bundle. So if you look at all the unit covectors, so this is if your manifold is dimension n, this is an Sn-1 bundle over your n manifold. So it's 2n-1 dimensional. Of course, it's well known on any tangent bundle, there's kind of a canonical one form that's basically characterized by the property that if you have any other one form alpha on M, lambda is a one form on the cotangent bundle. So if you have any one form on the manifold, that's a section, that's a map from M to the cotangent bundle. So you pull back this thing on the tangent bundle, cotangent bundle to M, you'll get a one form on M, and of course it's going to be alpha. So it's kind of the defining property of this Liouville one form. And in Hamiltonian dynamics, this is kind of the main thing you use to get a symplectic structure on the cotangent bundle. And it turns out that if you restrict this one form to our unit cotangent bundle, it turns out to be a contact form. So basically what we've done is we've given you a natural contact structure on the unit cotangent bundle. And notice that if you have two manifolds that are diffeomorphic, then the diffeomorphism between them gives you gives you a map between their cotangent bundles that basically preserves this lambda, and it actually is going to wind up then taking the contact structure on one of these unit cotangent bundles to the contact structure on the other one. So that's kind of an easy observation. And Arnold has this conjecture that basically two manifolds are diffeomorphic if and only if the associated contact manifolds are actually contactomorphic. So if this conjecture is true, it basically says you can study the topology of M by trying to understand the contact geometry of the unit cotangent bundles. And that anytime you have a geometric structure, there's usually all sorts of extra things you can study, like ray vector fields, contact homology, all sorts of various things the extra structure gives you. So I should actually point out, Arnold never explicitly made this conjecture, but he made several conjectures that are essentially equivalent to this statement. And this is one interpretation a lot of people have of those statements. OK, so I actually wanted to talk about submanifolds, not just the manifolds. So let's move on and do that. So suppose we have a submanifold n of our manifold M. We can actually associate a natural Legendrian submanifold of the unit cotangent bundle as follows. So just given n, you look at the unit conormal bundle. So you look at all the covectors, unit covectors, so the elements of W, who vanish when restricted to the tangent vectors to n. It's very easy to kind of work out. This thing is actually, if M has dimension n, this thing will also have dimension n. So it's an n minus 1. So it actually has, it's a n minus 1 dimensional submanifold of a contact 2 n minus 1 dimensional manifold. And it turns out to be Legendrian. It's actually tangent to the contact planes, or contact hyperplanes. And again, it's very easy to see that if you have any isotopy, any smooth isotopy between n and n prime, then the lifts L sub n and L sub n prime are actually Legendrian isotopic. So again, you can use you can use the geometry of, you can try to use the geometry of the Legendrian lifts to study the original isotopy of these submanifolds. And again, kind of a relative version of the Arnold conjecture is that two submanifolds are isotopic if and only if their lift to the unit cotangent bundle are Legendrian isotopic. This might seem like a very optimistic conjecture, and except in extremely trivial cases, it hasn't been proved at all. But I'd like to give you some evidence toward it in the next couple of slides. So going back here, this works for any submanifold of any other manifold. But let's just restrict to a very special case. So suppose you look at knots, say K in R3, and look at their conormal lift. So what does that give you? Well, the manifold, our contact manifold W, is just R3 cross S2, the unit cotangent bundle. And the unit conormal lift, well, it's going to be a S1 bundle over K, and it's oriented, so it's actually going to be a Legendrian torus in that manifold. So back in 2005, actually a few years before, Tobias Ekholm, Michael Sullivan, and I developed an idea of Eliashberg and Hofer of Legendrian contact homology, and actually proved that this is a well-defined invariant in particularly that space, R3 cross S2. The idea of Legendrian contact homology is something you can define for any Legendrian in any contact manifold, but I think various details of the rigorousness of that definition are still being worked out. But at least in this particular manifold, there's some very nice properties of it that allow you to actually prove everything works just fine. So also in 2005, Lenny Ng had basically looked at the ideas of contact homology and said, OK, forget all the analysis, forget making the real ideas of contact homology work. Let me guess what the answer is. Let me find a combinatorial way of describing Legendrian contact homology in terms of braids. And then I don't really care if it's actually contact homology. Let's just use that invariant to study things. And he actually wound up writing down an invariant. And he was able to compute it for lots of knots. And it actually distinguishes almost everything he ever looked at. Well, actually, it distinguishes everything he could actually compute. So it's actually quite possible that the invariant, this combinatorial invariant that he defined, is a complete invariant of knots. It distinguishes all knots. In particular, it encodes information like the Alexander polynomial. It doesn't maybe encode the A polynomial, but you can see bits of the A polynomial or relations with the A polynomial. It distinguishes the unknot, does all sorts of great things. Kind of a, I say, at this point I said maybe much information about the Jones polynomial. The reason I say maybe is kind of the funny thing is Lenny was able to find connections with almost every knot invariant you can think of. accept the Jones polynomial, but physicists predict that the thing it's supposed to be related to is the Jones polynomial. So people are still trying to really work out those ideas and those details. But the point is, it's a very powerful invariant. You might wonder, why do you really care about a complete invariant? We already have things like fundamental groups and peripheral structures and all sorts of things like that, but they're very hard to use. Well, this invariant also is very complicated. But one reason that you might care about this thing being a complete invariant is, a few years later, actually to tell the truth, it's only a year or two later, but it really took us a long time to write it down. So Ekholm, Ng, and Sullivan and myself were able to prove that Linné's combinatorial thing really was, not just inspired by, but really was, honestly, the contact homology. So if you actually can prove that this combinatorial invariant of Linné's is a complete invariant of knots, that means the Legendrian contact homology is, which means the conormal lift of Legendrian knots is are different if the knots are different. So in other words, Arnold's conjecture would be proved in this case if you could prove that this combinatorial invariant is a complete invariant of knots. So it's not necessarily that we want a new complete invariant of knots. It's the idea that you've realized Arnold's conjecture in one case if you can kind of prove that. And I actually think we might not be all that far off from verifying this. There's lots of good evidence for it, and I think a few people at least have some ideas about some approaches. And again, I would like to emphasize, Arnold's conjectures seem ridiculously optimistic. And the only thing you could really check them for is maybe points in surfaces or something. But this would be the first non-trivial evidence that it actually might be true in more generality. OK, well, now for the main result in the talk, and that's actually the existence question in high dimension. So at this point, hopefully I've convinced you, contact structures show up all over the place. They've got lots of interesting applications. So once you're interested in the structure, there are some very, very basic questions you might want to ask. And the very first one you might want to ask is about the existence of a contact structure. So before I can state the proper existence question, I need to give you a little bit of background. So suppose you have a contact structure on your manifold. So C is a contact structure in a manifold. And remember, I'm actually being slightly restrictive here. I want my manifold to be oriented, and I want my contact structure to be oriented. If that's the case, you can always split the tangent bundle at every point in terms of the contact hyperplanes and R. In fact, that's not just a pointwise splitting. You actually split the bundles as the contact hyperplanes direct sum the trivial R bundle over M. Well, if you write C as the kernel of a one-form alpha, then that one-form alpha, when I take d of it, remember d alpha to the n is going to be non-zero on those contact hyperplanes. That was our contact condition on the first slide. So that's a non-degenerate two-form on C, so it's a symplectic structure. And it's well known that given a symplectic structure, there's always a compatible complex structure with that symplectic structure. So we basically get this complex structure J on our contact hyperplanes. And the main condition I want about that compatibility is just given here, that V, JV, is positive for any non-zero V. So what does this give us? Well, this gives us, if we have a contact structure, this gives us a splitting of the tangent bundle in terms of a complex subbundle and a trivial bundle. And we're going to define an almost contact structure as a hyperplane field on the manifold together with a complex structure on that hyperplane. So that's an almost contact structure. And this is a necessary condition if you have a contact structure. If you want your manifold to have a contact structure, it better have an almost contact structure. Okay? And this is a purely kind of bundle theoretic condition, so you can study it using obstruction theory and so forth. So this is something you have some hope of answering without using geometry, just using algebraic topology ideas. And of course, as we just said, a contact structure gives a well-defined homotopy class of almost contact structure, obviously. Well, I guess it's not obvious. I guess you do have to know that there aren't any two J's on here are actually homotopic, but they are. And our main question now, the main existence question is, given an almost contact structure on a manifold, when is it homotopic to a contact structure? So is it true that it's always homotopic or not? So some background. In dimension 3, again, everything's oriented. Any oriented plane field on M is actually an almost contact structure. That's easy to see. Just pick a metric on M and define the complex structure to be rotation by pi over 2. And that, of course, is going to give you an almost complex structure on your plane. So any plane field is an almost contact structure. And any contact structure is has an underlying hyperplane or plane. And anyway, so almost contact structures are the same thing as oriented plane fields. And we have the existence results back from the 1970s. So the first existence result was Martinet, who proved that any closed three-manifold has a contact structure. And later, not that it looks like it from the dates, but Lutz actually proved that any homotopy class of plane field has an almost contact structure in that homotopy class of plane field. And it turns out every three-manifold, by the way, has infinitely many different homotopy classes of plane field. So basically, Lutz says there's infinitely many different contact structures on any manifold. So this is a three-dimensional situation, and at least the basic existence question was worked out, again, in early 1970s. I'd like to tell you a little bit more about the three-dimensional setting, because we're going to need this when we talk about the five-dimensional setting. So once you have the basic existence things answered, you can ask, well, are there different contact structures in the same almost contact structure? And that was actually answered by Bennekin, but let me describe Eliashberg's approach. You say a contact structure is over-twisted if there's a disk that looks like this. So what does that mean? You basically got this gray disk sitting in your manifold so that it's tangent. So the contact planes are tangent to the disk all along the boundary. So this is kind of the most basic over-twisted disk, but you can imagine other types in there. But if you have that sort of disk sitting inside your manifold, you say your contact manifold is over-twisted. If you can't see any disk like this, then you say your manifold is tight. And Eliashberg, once this was defined, Eliashberg proved that there's a one-to-one correspondence between plane fields on the three-manifold and isotopy classes of over-twisted contact structures. So in other words, every plane field is homotopic to an over-twisted structure, and every two over-twisted structures in the same homotopy class of plane field are actually isotopic as contact structures. So a complete classification of over-twisted contact structures on three manifolds. And again, there's infinitely many different over-twisted things. So tight contact structures are much more subtle, and pretty much all the applications I talked about earlier rely on tight things, not the over-twisted things. So again, it's not surprising. The over-twisted ones are clearly related to algebraic topologies, the almost contact stuff, where the tight ones are much, much more subtle. So let me give you a few ideas about what we know about those. So there's a unique tight contact structure on S3. Again, this was due to Eliashberg. Again, he's one of the people that really started all these things going early on. Then in 2000, Kohanda and Emmanuel Giroux gave various classification results, say, on Lin spaces, torus bundles, solid tori, various simple manifolds. But I guess, well, anyway, it's up here. It was long thought, I think, that every three-manifold must have a tight contact structure, and it turns out that's not the case. So Kohanda and I were able to show that in 2000. We actually found one manifold that didn't have a tight structure on it, and then Liska and Chipschitz were able to generalize that and show there's a very simple family of manifolds that don't have tight contact structures on them. As far as we know, that might be the only examples. Anyway, there's many other results of classification on ciphered fibered spaces by lots and lots of people. I think these are the major kind of players, but there's a few others maybe. I just kind of emphasize this because this is actually one of the kind of main questions in three-dimensional contact geometry right now. Basically, once you put together all the results here, we understand the existence question, at least completely, for tight structures on all ciphered fibered three-manifolds. And the main other class of three-manifolds you might be interested in, or that are out there, are hyperbolic manifolds. And we really know virtually nothing about them. You give me a hyperbolic three-manifold, I can probably construct a tight structure on it, but I can't say there's any big class of hyperbolic three-manifolds that I could just guarantee on that entire class there is going to be a tight contact structure. So I mean, one of the problems is people really don't know how fundamental groups interact with the contact geometry. And anyway, there don't even seem to be very many good approaches to answer this question. OK, so now finally let's move on to the five manifolds. So given an oriented five manifold, it turns out not all oriented hyperplane fields have a complex structure on them. So there's an obstruction. So a five manifold will have an almost contact structure if and only if the second Stiefel-Whitney class has an integral lift. Okay. So we went into a lot more details about this afternoon, but this is a fairly simple bundle theory. Allows you to kind of get this obstruction. And it's, in fact, the only obstruction to the existence of an almost contact structure on a 5-manifold. And it turns out that the homotopy classes of almost contact structures are in 1-1 correspondence with integral lifts of W2. Well, that's at least if the second homology doesn't have 2 torsion. When there's 2 torsion, there's a little bit of ambiguity there. But again, so we understand the existence problem for almost contact structures fairly well. And I didn't put it on the slide, but I should mention there are examples of 5-manifolds where W2 does not have an integral lift. There's lots of simple examples you can kind of build by taking some disk bundles over spheres and gluing them together in various ways. So yeah, and if you go on past dimension 5, there are basically very similar results. In fact, in dimension 7, it's exactly the same. In dimension 7, an oriented 7-manifold has an almost contact structure if and only if W2 has an integral lift. Once you get to dimension 9 and above, the condition is much more complicated. But again, there's bundle theoretic ways you can kind of study it, algebraic topology ways to study the existence question for almost contact structures. So finally, let me get to the existence question. So the main result is that on an oriented 5-manifold, any almost contact structure is homotopic to a contact structure. So this is basically analog of the Lutz result in dimension 3. And this is proved by Castel-Pancioli and Presas, and independently by myself, both of them in 2012. I'll say a little bit more about that in a second, but first let me give you a little bit of results that led up to this. So the first kind of general existence result for 5-dimensional contact structures was by Huygens in 1992, who proved that for simply connected manifolds, every almost contact structure is homotopic to a contact structure. Huygens and Thomas actually generalized that a little bit to certain non-trivial fundamental groups, but it was still a very restricted class of them. And then, so actually, Castel-Pancioli Presas actually proved in mid-2012 kind of a general existence result if there's no 2 torsion, but they couldn't get the general existence result. And then about the same time, we were able to both finish off the general case. By the way, the techniques are completely and utterly distinct. And what I'd like to tell you about today is basically my approach to this theorem. And just give a little sketch of the ideas. The main idea, or one of the main tools we use here, is the idea of open book decomposition. So an open book decomposition on a manifold of any dimension is basically a pair B pi, where B is a codimension 2 submanifold, such that its normal bundle is trivial. So it has a neighborhood that looks like the manifold, the B cross D. And there is a fibration of the complement of B over S1 such that, well, at least in the neighborhood of the binding, it looks like this. It basically has a very special form. So the fibers of the fibration are called pages of the open book, and the B, the submanifold, is called the binding of the open book. Something that will be important for us is actually reformulate open books in terms of other notions. So notice that whenever you have a fibration over the circle, MB is a fibration of the circle, if you kind of cut along one of the fibers, you just get the fiber cross interval, because it's a bundle over the interval, so it's trivial. And you can recover the bundle over the circle just by gluing kind of the front face to the back face of your X cross 0, 1. So you can recover the complement of the binding just by kind of a mapping cone construction with some diffeomorphism of the page. Mapping cone, mapping torus construction. And it's actually very easy then to glue back in the neighborhood of B, especially in higher dimensions, in a unique way. So basically, the open book is essentially completely described by a two n-dimensional manifold X and a diffeomorphism of that manifold. And that diffeomorphism is called the monodromy. So let me give you some very easy examples. So the simplest possible example, and the only one I can probably draw in detail for you, is if you take S2 and you take the binding B just to be the north and south pole. It's a codimension 2 submanifold. If you remove them, the complement of the north and south pole is simply an annulus, and of course an annulus fibers over the circle. So very simple. Let's look at a slightly less simple example. So if you take this wedge, it's kind of like a milk carton from grade school or a doorstop or something. So you have this wedge, and if you identify the top of the wedge to the bottom of the wedge and the front to the back, I claim you get S3. And it's very easy to see that. You can see that because if you split it along, say, this green disk, right? If you split along the green disk, notice, well, what do you have when you do these identifications? This green square becomes a torus. And if you take kind of a triangle here, that triangle, when you identify it, is a disk. So this is a torus with a compressing disk. And in fact, you can see an S1's worth of disks in there. So this is a solid torus on this side. This is a solid torus on this side. And the meridians come together in a single point. It's essentially S3. By the way, this is a really amazing picture. You can see all sorts of things. You can see the hot vibration in here. You can see various open books in here. You can see lots of interesting things in this nice, simple picture of S3. In particular, notice, take these pink curves, so the edges of the wedge. When you glue those up, those are two circles. You can actually easily convince yourself those two circles happen to be the hot flink in S3. And if you remove the hot flink from S3, then in this picture, what's left? Basically, then it's a torus cross interval. And of course, a torus cross interval has lots of vibrations over the circle. And it's not too hard to find, in fact, two of them that come into the binding the right way, like we said on the previous page. So this is a very nice explicit open book on S3. OK, so we're going to use open books to try to construct contact structures on 5 manifolds. So the main question is, do they exist? And well, luckily, back in the 70s, Frank Quinn was able to show that on an odd dimensional manifold, basically they always exist. In fact, they always exist with pages that have handle decompositions where the handles have dimension n or less. And that's going to be very important for us as we move on. There were many precursors. Maybe I won't go into all the details here, but lots of things led up to this. But Quinn was the one that kind of finally got the exact statement in all dimensions. By the way, open books exist on even dimensional manifolds too, but well, on some of them there's actually an algebraic obstruction. But there's a precise algebraic obstruction that if it vanishes, you can construct open books. If it doesn't, you can't. By the way, that's maybe true in all dimensions but 4. I'm not sure if it's known in dimension 4 or not. Anyway. All right, so they exist. And they have a nice structure. So the second tool I'm going to need to construct the contact structure is the idea of a Weinstein structure on an even dimensional manifold. So a Weinstein manifold is the following. So it's basically a triple lambda v f such that d lambda is a volume form on W. So in other words, d lambda is a symplectic form. Right? So if it's a symplectic form. V is a vector field that satisfies this equation, so it's kind of the Liouville vector field of this Weinstein structure. V needs to point in along the bottom and out along the top. And F needs to be a Morse function such that V is gradient-like. So as you flow along V, F is increasing. And also, of course, the boundary of W, the lower and upper boundary, are regular level sets of our function. So this is a Weinstein structure on a manifold. And the main thing that allowed my proof to kind of go through was this great result of Kai Chilibach and Yasha Eliashberg just a couple of years ago. And they proved that forget the word flexible right now, I'm not going to go into a lot of details here, but two special types of Weinstein structures on W are going to be, there's going to be a one parameter family connecting these two of Weinstein structures if the following things are true. If the lambda i's induce overtwisted contact structures on the lower boundary, there's a family of functions interpolating between f0 and f1 such that all those Morse functions, they're a family of functions such that they're Morse except at isolated points. And isolated points, you have births and deaths, but you never have index 3 critical points born, or index 4 actually. And finally, you've got to have a non-degenerate 2 form that interpolates between d lambda naught and d lambda 1. If you have these 3 conditions, these are 3 necessary conditions. If you have them, then it turns out that there's a one parameter family of Weinstein structures that connects the lambda naught, well, the 2 Weinstein structures. So I think with this said, we can start the actual proof. And the first step in the proof is that given an almost contact structure, J, on a 5 manifold, then there is an open book decomposition, which was given to us by Quinn. But moreover, you can find it in such a way that that the J from eta, so basically you can homotop the eta very close to the pages of the open book, so that J restricts to give an almost complex structure on the pages And when you have A that intersect the binding, it's actually a contact structure. So you can actually set up a very, very nice situation to relate the almost contact structure, and in particular the complex structure for the almost contact structure, to the open book. With this in mind, we're going to do the following. So here's my manifold M. And well, remember, M has an open book, and the open book can be described by our monodromy phi. Some monodromy phi, this is a diffeomorphism of the pages of the open book. And I'm going to break M up into 3 different pieces. So first of all, let x prime be a ball embedded in the page x. And we can isotop our monodromy so that it fixes that ball. And let x double prime be the complement of the ball. Okay? Now, notice M is now broken into 3 pieces. The first piece is just the neighborhood of the binding. So this is just B cross D2. The second piece is the mapping torus of the ball. Oh, sorry. Yeah, the mapping torus of the ball, the x prime. So this is just a ball across S1. And the last piece is what looks like the complicated piece. It's everything else. It's the mapping torus of everything else. So we've broken M into these 3 pieces. So M is just the union of those 3 pieces. So again, very simple, and then a moderately complicated piece. Okay. And what we're going to do is we're just going to build the contact structure step by step. We're going to build the contact structure on here, extend it to here, and extend it to there. Couldn't be simpler, right? OK, so how do we do that? Well, on the lower piece, that's actually very nice. There was a result of Desant Pancholi and myself from a couple of years before that said basically there is a contact structure on this piece such that on the boundary of the ball at each point, that's a 3-sphere, that's a 3-dimensional submanifold of the boundary here, the contact structure on the 5-manifold restricts to give a contact structure on the 4-ball, and that contact structure is actually an over-twisted contact structure. By the way, in kind of little disclosure here, we're actually having to write an erratum to this paper, but luckily the result that's used here is an epsilon perturbation of the proof that's in the paper works. So this is fine. Anyway, so we have our contact structure here, and we know something about what happens at the upper boundary of each of the pages that exist down here. So now let's try to extend this across C double prime. So how do we do that? Well, so remember, CW prime is just x double prime cross 0, 1 with the front and back glued to each other. So it turns out that Eliashberg and Weinstein both told us how to put a Weinstein structure on W0, and you can use phi to transfer that Weinstein structure to W1. So basically, I have a Weinstein structure on x double prime cross 0 and x double prime cross 1. And then basically, Chilibach and Eliashberg's result tells us how to extend that to get a Weinstein structure on all the WTs, so all of the x double prime cross t's in this product. By the way, I put a little asterisk here because if I had time, I was going to explain more. I say you just apply Eliashberg and Chilibach. Well, notice, to apply Eliashberg and Chilibach, one thing you needed to know is that the Morse function that I had on W0 and the Morse function I had on W2 could be incorporated in a family of functions where there was no index 3 critical points born. And unfortunately, in dimension 4, that's not true. So you actually have to do quite a lot of work. So this is probably some of the hardest part in here. You have to do quite a lot of work to actually change the open book in such a way that you can achieve the fact that there's no index 3 critical points being born along the way. But you can do that. And then Eliashberg and Chilibach give you these lambda t's. These are the 1 forms that show up in your Weinstein structures. And then it's very easy to check that k times dt, where t, of course, is the coordinate in the interval direction, plus the lambda t's. It's very easy to check that's a contact form as long as k is large. And it's also very easy to see that this actually glues up with the contact structure that we built before. So basically now we have a contact structure on these 2 pieces, and we just have to extend it over the NB. And here we're going to use Eliashberg's result again. So from the previous steps, so the boundary of the neighborhood of B is B cross S1. And for B cross point, so that's a so that's a 3-manifold sitting inside of here, and it's also the boundary of one of the pages, right? And as the boundary of one of those pages, it gets an over-twisted contact structure on it. So since we have an S1's worth of pages, we get an S1's worth of contact structures on B, and those contact structures are all over twisted. And Eliashberg basically tells us that those contact structures bound a disk's worth of contact structures on B, and I can use that disk's worth of contact structures to extend this thing over the neighborhood of B. So I mean, you just have to write down, it's basically write down the right form, and it works. And so this is it. This gets us our contact structure on the whole manifold, and that's the existence. I mean, well, I didn't carefully go through here and tell you why is this homotopic to the original one, but that's actually not a very hard part to do once you have the construction in place. So what are the things that are left to kind of consider? Well, what about the general existence results in dimension 7 and higher? As I think I alluded to at lunch today, there are several people who have approaches to this. In fact, there's a group of people that I think are very close to announcing maybe that they can actually do this. Is there a tight versus over twisted dichotomy in higher dimensions, in dimensions greater than 3? There's some conjectures out there about what that should be, but at the moment I don't think too many people have any real good ideas about what it should be. And can we classify contact structures on any manifold above dimension 3? I mean, we have various existence results, but we have absolutely no classification results. It seems like the situation is much, much, much more complicated than dimension 3. Even on spheres in dimension 7 and above, there's usually infinitely many different contact structures, and no idea if this should be everything or if there should be other families of them or what. So classification seems like it's going to be very difficult in higher dimensions. And probably the question I may be most interested in is how can we use, what can we learn about the topology of manifolds and submanifolds by using contact geometry? In other words, using this conormal lift idea, and how can we use Legendrian submanifolds to study isotopy problems in general manifolds? And again, I think there might be a few things in the near future, but I think there's a long way to go before we understand too much about this. And I think that's maybe a place to stop. Mm-hmm. Well, so when he first reinterpreted the contact homology in terms of this combinatorial thing, and he then has a piece of that combinatorial thing, and that's the amazing thing, is maybe even a small piece of the whole thing is enough to distinguish everything. So he has an interpretation of this combinatorial piece, a piece of this combinatorial invariant in terms of what's called, I think he calls it the chord algebra. So it's basically kind of, you're looking at kind of strings that are embedded in your manifold with their endpoints on the knot, and you have various relations that show up here. And it turns out this is very, very closely related to the fundamental group of the manifold. Now, unfortunately, in a complicated way. Basically, you take the fundamental group of the manifold, you look at the group ring associated to it, you look at kind of a free group generated by that, you mod out by some relations. So it's moderately complicated. But the point is, it is defined in terms of the fundamental, you can define it in terms of the fundamental group of the manifold. And we know the fundamental group, at least for a prime knot, determines the knot complement. Right? So the hope is that you can kind of, that basically, this construction, this group ring construction and so on. By the way, groups are not determined by the group rings. But is that true for 3 manifolds? Does anybody know that? I've been trying to figure this out for a while. Are 3 manifold groups determined by their group ring? Groups are not in general, but 3 manifold groups might be. And in particular, maybe are not complements. The fundamental groups are not complements determined by their group ring. If they are, I think there's a very good chance that you might not lose too much information when you take these other quotients. And so this is one approach you could try to get at that question from. As far as it's the only approach I know. I think Lenny might have some other ideas, but this is certainly what I've been thinking more about lately. But yeah. So it's, yeah, to tie it back to what we know are complete invariants already. Yeah. I don't know. I haven't got far enough. I mean, but again, even if you're just using the fundamental group, if you could show that's a complete invariant for prime knots, that's already a pretty nice, step. But I mean, it is true that also in this chord algebra, meridians and longitudes do show up at various places. Now, they don't seem to show up in places that you might want to see them, so I'm not sure that we're really going to be able to recover the whole peripheral structure. But again, I can't, I don't know. I'm hopeful that you can recover the fundamental group. After that, we'll have to see. But.